Fine-tuning a huge language model sounds kind of impossible. You look at a model with billions of parameters and think, okay, if I want it to behave differently, I probably have to update all of those numbers. What if I tell you it doesn't need to be the case? LoRA does something very clever. It says don't retrain the whole model, freeze it. Keep the original weights exactly where they are. Then add a small trainable update next to them. And that small update is often enough to adapt the model to a new task. Hi, welcome back to my channel, and if you're new here, my name is Anna, and on this channel I explore machine learning concepts in a simple and intuitive way. Let's start with the problem. Inside a neural network, a lot of the work happens in a big weight matrices. When an input comes in, the model multiplies it by these matrices, layer by layer, to produce the next representation. In full fine-tuning, we update the original weights of the model. That sounds simple, but it becomes expensive very quickly. Because during training, we don't only store the model's weights, we also need gradients, we need optimizer states, we need activations for backpropagation. So the memory cost is much bigger than just loading the model. This is why fine-tuning a large model can feel impossible on a normal GPU. Not because the idea is complicated, but because we are trying to move too many numbers at once. So LoRA changes the question. Instead of asking, how do we update this giant matrix? It asks, can we leave the giant matrix frozen and learn a small correction? Normally a layer takes an input X and multiplies it by a weight matrix W. With LoRA, we keep W frozen. Then we add a trainable update. And here is the LoRA layer. Here W is the original model weight. It doesn't move. The matrices A and B are the new trainable parts. And the key is that A and B are much smaller than W. So instead of training the entire large matrix W, we train two small matrices whose product behaves like an update to the original weights. That is the whole trick. Let's make this visual. Imagine this big rectangle is one weight matrix in the model. In full fine-tuning, we would change this entire thing, but with LoRA, this big matrix is frozen. Now we add two smaller matrices. One is skinny in one direction, the other is skinny in the other direction. Then we multiply them. They create an update that has the same shape as the original matrix. But we never had to train a full update matrix directly. We only trained the small factors. The phrase low rank basically means that this update is constrained. It cannot represent every possible change to the model. It represents a smaller, structured family of changes. And the surprising thing is, for many fine-tuning tasks, that is enough. Now let's see the satisfying part in code and look at one large layer. A 4096 by 4096 matrix has over 16 million parameters. If we fully fine-tune it, all of those numbers can change. But with LoRA, we don't train the full matrix. We train two smaller matrices with rank 8. One 4096 by 8 and one 8 by 4096. So instead of 16 million trainable parameters, we get only 65,000. That is less than 0.5%. And this is the key idea. LoRA keeps the large pre-trained matrix frozen and learns a tiny update next to it. Now we attach LoRA layers to selected parts of the model. Notice what is trainable here. The original weight is frozen. Only A and B are trainable. And this is the moment where LoRA becomes real. You see that less than 1% of the parameters are trainable. The model still uses the original knowledge from the pre-trained weights, but the adaptation happens through a tiny number of new parameters. This is why LoRA is everywhere in modern fine-tuning. It makes the experiments cheaper, it makes adapters easy to save and share, and it means we can have one base model with many different behaviors. You can imagine one frozen base model and then small adapters for different tasks. One for legal text, one for medical notes, one for customer support, one for a specific writing style. Instead of copying the entire model every time, we keep the base model and swap the adapter. This is also why LoRA is so popular in open source fine-tuning. It lowers the barrier. We still need a good setup and good data, but we don't need to train every parameter in the model. But LoRA is not magic. First, it still depends heavily on our data. If our data is noisy, biased, or too small, LoRA won't magically fix that. Second, the rank matters. If the rank is too low, the adapter may not have enough flexibility. If the rank is too high, we train more parameters and lose some of the efficiency. Third, LoRa is not always as strong as full fine-tuning. Sometimes, if we really need the model to deeply change, updating more of the model can help. So the practical way to think about LoRa is not this is always better. It is this is a very strong trade-off. You get a lot of adaptation for a much smaller training cost. So here is the whole idea in one sentence. Full fine-tuning changes the model. LoRa freezes the model and learns a small low-rank update. That small update is made from two trainable matrices. And because those matrices are much smaller than the original wave matrix, training becomes cheaper. So when people say they fine-tune a large language model on a small GPU, very often the trick behind the scenes is something like LoRa. I also have videos on vector search, embeddings, and RAG if you want to go deeper. If you found this helpful, feel free to like the video and leave a comment. It really helps more curious minds like yours discover the channel. And if you want more videos like this, consider subscribing so you don't miss future videos. As always, all the resources, including the code, will be in the description below. Thanks for watching and I will see you in the next one. Bye!